Here's our project for today. We are standing a certain distance away from a tower that's a fixed 100 feet tall, and we want to look at the relationship between how far we're standing from the base and our angle of elevation to the top of the tower. So the measurements that we have are theta, which is going to be our angle of elevation to the top of the tower. Angles of elevation are always measured from the horizontal up to the thing that you're looking at. Our adjacent side is going to be the distance in feet that we're standing from the base of the tower. We're interested in figuring out what happens to theta as we move closer to the base or farther from the base. What we want to do is first speculate without making any calculations what's going to happen to theta as we move closer, what's going to happen to theta as we move further away. So go ahead and pause the video right now, make some guesses about what's going to happen, and then we'll come back and make some calculations. Welcome back. So we're going to figure out how to make some calculations, deciding how far we are from the base of the tower, and we'll calculate what the angle of elevation to the top of the tower is. So I started with something right in the middle. We just learned about our iconic triangles. So if we start with an adjacent side of 100 feet and the tower is 100 feet, then we're dealing with an isosceles right triangle. And we know that we'll have a 45-degree angle. We're going to take that as our baseline, and then we're going to move farther away from the base and closer to the base and see what effect that has on the angle. That just means we need to pick some values to move as we move away from the base. So on this side, let's go to 150 feet away from the base. So I'm going to have an adjacent side of 150. Our opposite side is going to be the 100, and then we can calculate our angle. Since we have an adjacent side and an opposite side, it makes sense to use tangent. We're looking for an angle, so we know we're going to use tangent inverse. The setup would be tangent of theta is opposite over adjacent. So to solve for theta, we'll need to use tangent inverse of opposite over adjacent. What we're going to do is we're going to fix our opposite at 100 and adjust our adjacent. That's not good. It's the same abbreviation. And modify our adjacent to different values and just use that to calculate a bunch of thetas. So for 150, our theta is going to be tangent inverse of opposite 100 over adjacent 150. We'll grab our calculating machines, and we'll do a tangent inverse of 100 over 150. So our angle decreased down to 30, we'll call it 34 degrees. We'll round to the nearest degree. What we want to do is move a little bit further away and see what happens to the angle. So I'm going to use the same calculation, just adjusting or modifying our adjacent side. Here's one sample calculation. We're going to grab our calculating machines and change the denominator in that tangent inverse. So I'm going to do tangent inverse of 100, that's our fixed opposite, and we're going to go up to 200 feet. Let's be 200 feet away. And our angle has decreased again to 27 degrees. So at 200 feet, our angle of elevation drops down to 27 degrees. Let's just do a couple of more to get a feel for what's going on. So we can see that as we move away, as expected, the angle of elevation gets lower because the farther away we are from the tower, the shorter the tower looks. So the less we have to look up to see the top of it. So at 250 feet, we were at an angle of 22 degrees. And at 300 feet, we were at an angle of 18 degrees. One of the things that we want to point out here is that as we move away, notice we're moving away in 50-foot increments. The angle is changing by a different amount each time. We don't have a linear relationship between the adjacent side and the angle theta. When we are in the first 50 feet, we move away, we drop from 45 to 34. So if we grab our calculating machine, 34 minus 45 means we decreased by 11 degrees. But the next 50 feet, from 150 to 200, we ended at 27, we started at 34. That was a decrease of 7 degrees. And then 27 minus 22, we have a decrease of 5 degrees, and then a decrease of 4 degrees. So the amount of decrease that we see as we move further away is less. It was a big change in the angle from 100 feet to 150 feet, but not much change from 250 feet to 300 feet. Take a minute and think about how that matches with your intuition, because the further away you go, the less change you're going to be seeing. Now let's jump to the other side. I'm going to do the same thing. We're going to move ourselves closer to the tower. So I'm going to do the same calculation, only I'm going to modify our, I'm going to be modifying our adjacent, only this time I'm going to be using a number less than 100. We expect as we move closer to the tower, our angle of elevation is going to increase because we're going to be close to the tower. It's going to be harder to look up. So we did 50-foot increments over here because we had lots of space, but we don't have a lot of space on this side. Let's drop it down by 25. So what happens at 75 feet from the tower? We'll do a tangent inverse of 100 divided by 75. 53 degrees. As we suspected, the angle of elevation went up. Let's move into 50 feet. Do the same calculation for 50 feet from the tower, and our angle has gone up again, 63.4, so we'll call it 63. When we stand 25 feet from the tower, our angle of elevation is going to be up to 76. Now we run into a problem. I'm taking these 25-foot steps. If I take a step all the way down to 0, that's going to be a problem. Don't try this at home, but I'm going to try to divide by 0. And you know what's going to happen. Our calculator is going to look at this 100 divided by 0 and say, dude, that's undefined, and it's not going to calculate it for me. Bias calculator, go to it. It's like, oh, the problem is right here. You tried to divide by 0. It's a good thing you're a math teacher. The math cops will not try to come and arrest you. So one of the things that we note is that if I try to plug in 0, we're not allowed to. We can't plug in 0 feet. But we can keep moving closer to the tower. Let's think about the case of us standing 0 feet from the base of the tower. So if we're thinking about this, we should be looking, we'd have to look straight up the side of the tower. It's debatable about whether we'd be able to see the top of the tower. Are we really looking at the top of the tower, or are we really just, or are we just going to be looking past it? So that's neither here nor there. We're going to be looking straight up the tower. And when we think about that, if our angle of elevation is going directly up, we could think of our angle of elevation being 90 degrees. Even though we can't plug in 0 feet, we can imagine that our angle of elevation is 90 degrees. So this is just what we arrive at if we're thinking about looking straight up at the tower. So here's us thinking about it. Now, we can't do that calculation. I can't plug in 0 feet away from the tower because it shows up in the denominator for my adjacent. Let's pick some values that are close to 0. So I can't do 0 itself, but what if I tried something very small, like 1? I get an 89.4 degree angle. Let's try something smaller than 1.5. I don't like not having a leading 0. So as we get closer, our angle is still going up. But notice that from this 1 to the 0.5, we went from 89.4 degrees to 89.7 degrees. It increased, but not by very much. Now we're going to start taking some bigger steps from 0.5 to 0.1, 89.7 to 89.9. Now I'm going to be standing 1/100th of a foot from the tower. And I'm going to keep putting a 0 in before the 1. And our angle does keep going up, but it's going up by not very much. And this does seem to match our intuition when we were thinking about what's going on with the problem. If we're standing exactly at the base of the tower, our angle of elevation is going to be directly up, and that's an angle of elevation of 90 degrees. So we can't plug in 0 feet, but we can plug in stuff that's close to 0 and see if it matches our intuition about what's supposed to happen. Note that once we have an adjacent side of 0, we're not even looking at a triangle anymore. So this is kind of a weird question. We don't have a triangle because I've got a right angle here. I've got a 90-degree angle here. That's a 180-degree angle. So I have 0 degrees to put at the top. I don't have a triangle anymore. I've just got 2 line segments that smashed together. My hypotenuse is exactly the same as my side opposite. My adjacent is dropped down to 0. We're not even looking at a triangle. We might, in some circles, refer to this as a degenerate triangle. But I don't really like that language. It seems kind of harsh. It's just a kind of triangle that's collapsed. Let's take a look at what goes on on the other side. So here we've got this 90-degree angle. If we're standing right at the base, how far away would we have to go if we ended up in here? Can we get a 0-degree angle of elevation? So we know that the farther away we go, the smaller this angle is getting. At 300 feet, it's all the way down to 18 degrees, which is still really steep. For this calculation, our adjacent side is getting larger and larger. So let's see what happens when we plug in larger and larger values. So instead of these little tiny adjacent sides, we want this to increase. So at 1,000 feet away, our angle of elevation is 5.7 degrees. At 10,000 feet away, we're taking big steps now. It drops down by, drops down by about a tenth, 0.57 degrees. That's a very shallow angle. So as we keep moving away by a factor of 10, we drop our angle down by approximately a factor of 10. It looks like we're going down by a factor of 10. We're far enough away that it's almost linear at this point. At a certain point, the calculator is going to run out of digits, but we're pretty far from that. This is 5.72. This little e and the -4 means times 10 to the -4. So that's 0.000572957. So it's saying There's too many zeros for me to display. I'm just going to tell you there's 3 zeros in front of the 5. It's 4 because we want this number in scientific notation. We want the number part to be between 1 and 10. Let's do this again. To the -5, to the -6. Every time we go away by a factor of 10, our angle drops down by a factor of 10 as well. What's going to happen is we're going to have to go very far away to get a 0-degree angle. We're not going to be able to make this a 0-degree angle. Eventually, we'll run out of digits on our calculator. Wow, you get a lot of... We can see that we're going to go pretty far. I'd have to put, it looks like we've got down to the -22. So you could probably go down to the -99 before the calculator runs out of digits. Well, what's going on is we're going very far away and still getting some very, very tiny, but still positive angle. We don't get all the way down to 0 until we are infinite feet away. So that's a little bit weird to think about. We can think of this 0-degree angle of elevation as us just not being able to see the tower. And on a long enough plane with good enough eyesight, we would have to be infinite feet away to not see the tower at all. And that's one of the ways that we can interpret what's going on with these calculations. Now, of course, we couldn't do this here on Earth because the Earth is round, and eventually when we're far enough away, when we're this far away, we'd actually have gone past the tower. We'd show up on the other side and pass it a bunch of times as we just go around. So we're going to have to move this somewhere to the astral plane and be really far away where everything can be flat. The Euclidean part of the astral plane. If you've been there, you know what I'm talking about. The context for all of this was that we know our values of sine, cosine, and tangent for 30, 60, and 90. So we know our sine, cosine, and tangent of 30, 60, or 45. I think I said 30, 60, 90 because I was thinking of triangles. 30, 45, and 60. These are the values that we get from our iconic triangles. And what we want to do is we want to add the endpoints of these. Not really the endpoints, but we want to add 2 more columns to what's going on here. So we have all these values. Let's just fill them in. What we want to do is add the endpoints. We've got 30, 45, and 60. We want to know all the way around that first quadrant. I want to include 90 degrees and 0 degrees. And I wanted to think about it rather than just calculate it on our calculating machine. One of the things that's helpful is to have all the decimal approximations of these values. We know that 1/2 is equal to 0.5. That one works out nice. We also know that 1 is equal to 1. That one's pretty easy too. But we should know that the decimal approximations of, say, √2/2 So the square root of 2 over 2 is 0.7071. That way it'll be easy for us to check on our calculator our memory of these values. We should check root 3 over 2. 0.8660, we'll call it. Looks like we got a square root of 3. We should recognize that. 1.732. Oh, that makes sense. 1.732, 0.8660. So sine of 60 is half of a tangent of 60. And root 3 over 3. We got 0.5774, we'll call it. So we just want to fill out some more values. We want to know what's going on at 0 degrees and 90 degrees. The reason that we want to do this is that we want to eventually take sine, cosine, and tangent out of right triangles and move them onto any angle. To do that, we need to know what's going on in the first quadrant really well. If we learn all our values in the first quadrant, it's really easy to translate the first quadrant into the second, third, and fourth quadrants. So if we learn 0 to 90 really well, we can easily move that into 180 out to 90 out to 360. And once we've got 0 to 360 really well, everything else is just a copy of 0 to 360. So that's your next goal. Figure out what the sine, cosine, and tangent of 0 degrees and 90 degrees are to fill out this first quadrant of our iconic triangles really well. These endpoints can get a little bit weird because our triangle goes away. When I adjust my adjacent side all the way down to 0, my hypotenuse just kind of collapses onto my opposite. My theta becomes a 90. I've got two 90-degree angles and a 0-degree angle. Not really a triangle. So stuff is weirder at the endpoints. Here we have nice, solid, iconic triangles. Easy to calculate sine, cosine, and tangent. Figure out what's going on at the endpoints. That way we'll know our first quadrant really well, and then we'll learn how to translate that into other quadrants. All right, that's going to do it for today. I will see you all on Tuesday. Everybody have a good weekend, and thanks for playing.